Hello everyone, I'm Eishi Arima from University of Tokyo. It's my great pleasure to have a chance to make a presentation virtually in Frankfurt here. Well, actually, this is the second talk for me in this conference. Well, this talk is about data management for hybrid memory system. Let's get started. Okay, here is a summary of this talk. The background is various new memory technologies are emerging, such as HBM and NVRAM. And because of their trade-offs, especially in terms of bandwidth and capacity, hybrid main memory design is promising. But sophisticated data management is essential to achieve both. The key observation here is the benefit of the fast memory highly depends on the access pattern, which is a kind of fundamental characteristic and should be considered when we decide whether or not to move a chunk of data. Here is a proposal pattern-aware staging that consists of helper threading inspired dynamic address sequence sampling, Bloom filter-based runtime access pattern detection, and a criterion to determine whether or not to move the data. And here is the evaluation result, which is quite promising. And here is the outline. Let me talk about firstly a background and motivation. The problem is the DRAM scaling is almost ending, and also the bandwidth of conventional DIMMs is quite limited in terms of both number of pins and also the bus per budget. But clearly we need more for both. And the promising alternatives are, one is non-volatile RAM for capacity scalability, and the other one is dissect DRAM for bandwidth scalability. However, they have fundamental trade-offs, and bandwidth of NVRAM is quite limited, and on the other hand, the capacity of the dissect DRAM is also limited. So our target is hybrid main memories, which is actually supported in many recent systems. And especially we consider this software-based data management. Those are prominent targets. And one open question is how can we exploit both the high bandwidth and the large capacity at the same time for both those systems. And here is the goal and focus. The goal of this study is achieving both high performance and large capacity on the hybrid memory-based systems. And our focus is coarse-grained data transfer optimization. We divide large data into chunk of data, and for each chunk, we try to copy large to fast memory and access it and write it back to the large memory. The prominent target structures are multidimensional arrays and also structural arrays. And here we focus on the trade-off between performance benefit versus the copy overhead. If the benefit is smaller than the overhead, we should apply the staging technique. And the key observation is the performance benefit versus copy overhead highly depends on the memory access pattern that is measured on the real system. And especially the benefit becomes relatively longer when the accesses are more random, sparse, and irregular. In case of random, the performance benefit is relatively much longer. On the other hand, for sequential access case, the benefit is smaller than the overhead. In that case, we shouldn't use the staging technique. And this observation is fundamental. So the bandwidth degrades considerably for sparse and irregular accesses due to significant conflicts on banks, channels, and row buffers, and also that cannot use cache line efficiently. This would happen for any kind of memory set technologies, including non-volatile RAMs. And in fact, recent technical reports show that significant bandwidth degradation for non-volatile memories for random accesses. So then why don't we take these characteristics into account when optimizing the data transfer? And then next, I will talk about the concept. So our proposal is called pattern-aware staging. That is software-based optimization accomplished by source-to-source code transformation. And here is the original code, original loop. And we transform it into staged code like this. Further, we transform like this way. This is a pattern-aware staging code. So that consists of lightweight pattern analysis. And if the staging is going to be effective, we will use staging, otherwise not. And the pattern analysis part here consists of 3 parts. I will talk about them in the next slide. The sampling is actually inspired by conventional helper thread prefetching. And the characterization uses this obtained addresses that consists of 2 parts. One is slide filter for regularity analysis and page address filter for sparseness analysis. And the stats of those structures are used for the decision making. If the access is irregular and sparse, we use staging, otherwise not. Next, I will talk about the sampling part. The usage is designate the target loop array using our newly introduced directive like this way. So original code plus newly introduced directive is shown in the figure. Then we transform it like this way. Firstly, we copy the outer loop structure like this way and put the decision branch. And here is a target loop, inner loop, and transformed and inner here. That is sampling and pattern analysis part. And the code with staging is inline here. That is just a copy. Currently, the transformation is hand-coded by following prior helper thread prefetching studies. Automation is a kind of future work. And note that the target chunk can be designated by a special function, and that is called just before the time, the directive. That is actually discussed in our paper. The next will be the sampling part. So our approach is inspired by the existing helper threads prefetching. That changes the target loop into a software prefetch code and can be automated by the compiler. Here is the original code. And the code is transformed into the load instruction using the same address. And that is launched just before the original code. And instead of issuing load instruction prefetches, ours just put the taken addresses into pattern detectors, like this way. So we replace the load instruction with the filter input. We have 2 different filters. Okay, next is about the characterization part. So to detect the sparseness and regularity is the goal. The approach is history-based detection. Check if input is recorded in the history or not, and register it if not yet recorded. So we have an address, ICE address, and that can be converted into the page address and also stride. If the page address is already appeared before and recorded in the history, that returns hit, otherwise miss. In the miss case, this page address is registered. Likewise, for slide access, the history is checked, and in case of miss, that is stored on the history structure. And frequent page address miss means that many different page address appears before. That means the access is quite sparse. On the other hand, frequent stride misses means that many different stride appears previously. That means the accesses are quite irregular. For example, in case of streaming accesses and also the stride accesses, only one stride appears on the history and always hit on the history or the address pattern. So we need an efficient data structure for this history structure in terms of both memory and search overheads. And why don't we use Bloom filter for this? The memory consumption is quite small, and also the search overhead is also small. And here the n is number of records. So assuming we set ABC blah 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 to the array or list data structure, we need an entry for each element like this way. So memory consumption will be order of n. On the other hand, for Bloom filter, we put everything together, so the memory consumption is quite small. On the other hand, when we try to test C from history, in case of an array or list, we need to check term by term, and it takes on average order of n such time. On the other hand, in case of Bloom filter, it requires quite short time, just AND operation is needed. So it's quite efficient in terms of both time and memory. So here is more details of Bloom filter-based implementation. So inputs are page address and strides, and outputs are hit and miss. And storage consists of bit array. And all elements are initialized. And set and test operations are based on the multiple hash functions, like this way. So that consists of bit array and also multiple hash functions. So one drawback is the fault detection, false position happens on this data structure. So in the right figure, W wasn't set before, but the test of W returned hit due to the hash function collision. But it doesn't matter if the impact is small enough and the probability is quite low. The filter parameters should be chosen carefully for this. And so we explore the parameter space and choose the optimal parameters. For this parameter space, we choose the optimal combination. So as for the number of sampling, 2K and 1K is enough for PAF and SF in terms of accuracy. And 256 byte is per each thread is also enough for both of the filters, which is small enough. And also the time for sampling and characterization is also short. It actually takes only the 0.04% of time compared with the 8 gigabyte round trip copy. So it's quite efficient. The next is I will talk about the decision making part. So we basically try to guess whether the staging is effective or not by use of the obtained pattern features. Basic idea is we consider break-even line. So here is the vector of pattern features. And on the plane, we divide that into speed up area and speed down area. And that is divided by the break-even line, where the performance benefit is equal to the copy overhead. And we also consider the threshold that determines the aggressiveness of the decision. And if the feature parameter vector is mapped below the break-even line, that means the speed up area, we should use a staging. Otherwise, not. Here is decision criterion. And this is the evaluation function, whether or not we should apply the staging. And here's a copy overhead. We omit the first stage or third stage of copy for such as the read-only case or write-only case, we can omit them. And the boost performance benefit can be modeled like this way. S is a scaling factor, and we consider only the RUT, that is a number of references per element on the chunk. Actually, this function is extensive part, and in the future work, we are going to update this part. For the rest of the part, we consider this linear model using the hit rate of these two different filter structures. And the coefficients here are trained beforehand. Here is a validation. We actually evaluated the performance impact of false detections and also detection accuracies using sparse matrix vector, and matrix is selected from Florida matrix suite and CRS format, and the proposed method applied to the source vectors. And here is the performance impact of false detection. Most of the false detections happen when the penalty is small, which is a good feature for our approach. And we also evaluated the detection accuracy 79%, which is a good number. And we can also trade off the false positive and false negative by scaling the threshold TH. Check our paper for more details regarding these points. And then next, I'm going to talk about the evaluation setup. We used a night landing-based compute node, and for the workloads, we use some from HPCC benchmark, and also choose from NAS parallel benchmark, and we also use some stencil codes. And we compared the large-only approach and NUMA control, and also hardware cache, and our proposal. The comparison with other studies are described in the manuscript in terms of qualitative comparison. And here is a performance comparison. Basically, we, at the best case, compared with large-only approach, factor of 3 performance improvement can be achieved with our approach. On average, factor of 1.9 improvement, which is a quite good numbers. And compared with the hardware cache mode, in the best case, we gained 41% of performance improvement. The fast memory is actually useless for stream code, and our approach avoided using it, and thus no speed down. On the other hand, for hardware cache mode that move data between those two different memories, even for this workload, and cause significant speed down. And here is one exception. Hardware cache works better than ours. But in terms of scalability in memory, ours is better. So hardware cache is successful in holding useful data for smaller problem, but if we scale the problem size of application, it would fail for holding useful data due to significant conflicts on the hardware cache fast memory. But ours is selectively allocate useful data on the fast memory, so that is conflict free. So if we could scale more, the data size more, so ours will be better. And in the paper, we have more results, such as 36% of memory traffic reduction were achieved compared with the hardware cache. So this must lead to the considerable energy reduction. And also, we evaluated the estimated and measured execution time. So errors have no impact actually on decisions. And here is a conclusion and future directions. We proposed a software-based data management concept called pattern-aware staging that consists of sampling, characterization, and decision making. And performance improvement is quite good. And here are next steps. Definitely, we will consider the compiler-based automation, and also evaluation on different kinds of systems such as DRAM plus Optane is of our interest. And also, we want to evaluate with more complicated real applications. And we are also planning to improve the decision-making criteria, such as covering the energy-aware decisions. Okay, that's it. Thank you very much for your attention. If you have any questions, please don't hesitate to contact us. Thank you very much.